Right now, at this exact moment, you are looking at the past. Not metaphorically, not poetically, literally. The screen in front of you, the light leaving it, takes a measurable fraction of a nanosecond to reach your eyes. The person sitting across from you at dinner is someone you have never actually seen in the present tense. You have only ever seen them as they were 1 to 2 nanoseconds ago, depending on distance. The moon you look up at is not there. You are seeing it as it was 1.3 seconds ago. The sun, 8 minutes and 20 seconds ago. Andromeda, the nearest large galaxy, the one visible to the naked eye on a clear night, 2.537 million years ago. You have never, not once in your life, seen the present. If confronting uncomfortable truths is why you're here, subscribe. What follows will not reassure you. There is a number that nearly every person alive has heard, and almost no one actually understands. 1 light year. Ask someone what a light year is and they will tell you it's a distance. They learned that in school. They know enough to correct other people when those people call it a unit of time. Actually, they say with the comfortable authority of the partially informed, a light year is a distance. It's how far light travels in 1 year. They nod. They feel the small satisfaction of knowing the thing. They move on. They are wrong. Not about the definition. The definition is accurate. A light year is, in fact, the distance light travels in 1 year, approximately 9.461 trillion kilometers, or 5.879 trillion miles. That part is correct. The error is not in the words they use. The error is in what they believe the number means, and in what they assume that meaning implies about the universe they inhabit. Because when most people hear 1 light year away, they picture distance. Static, manageable distance, like a very, very long road. A road with a beginning and an end. A road you could, in principle, travel down if you had a fast enough vehicle and enough time and enough fuel. They treat a light year the way they treat a mile or a kilometer, as a measure of space, as a gap that separates 2 points, as a quantity that describes separation in the way that all distances describe separation, completely, with nothing hidden inside it, nothing else implied. This is the belief that is wrong, and it is wrong in a way that makes the universe, the actual universe, the one you live inside right now, the one that contains you, fundamentally, structurally, irrevocably different from the one you believe you inhabit. Here is what a light year actually means, stated as plainly as language permits. A light year is not just a measure of how far away something is. It is a measure of how far into the past you are looking. Every single time you observe any object in space, through a naked eye, through binoculars, through the most powerful telescope humanity has ever constructed, you are not seeing where that object is. You are seeing where it was, by exactly the number of years equal to its distance in light years. 1 light year away means you are seeing 1 year into the past. 100 light years away means you are seeing 100 years into the past. 2.537 million light years away means 2.537 million years into the past. No exceptions, no approximations, no technicalities, no edge cases where the rule breaks down. This is not a rounding error or a limitation of current instruments or a consequence of using an imperfect measuring system. It is the fundamental operating condition of a universe governed by a finite speed of light. And the speed of light, 299,790,2,458 meters per second, is not fast enough. This is the sentence most people never let themselves finish, not because they don't know the number. Most educated people have encountered the speed of light. They know it is very fast. They know it circles the Earth 7.5 times in a single second. They know that relative to anything they have ever personally moved, a car, an airplane, a spacecraft, it is incomprehensibly fast. And so they assume that at that speed, the delays are negligible. The lag between what happened and what we see must be, at that speed, essentially zero. It is not essentially zero. The speed of light is the fastest anything in this universe can travel. It is the absolute upper limit, the cosmic speed limit with no exceptions, no shortcuts, no loopholes that have survived experimental scrutiny across 150 years of increasingly precise measurement. And at that speed, at the fastest speed that physics permits to any object, any signal, any form of information transfer, light from the Andromeda galaxy takes 2.537 million years to reach your eye. What you see when you look at Andromeda is Andromeda as it existed 2,537,000 years ago, before anatomically modern humans existed on this planet, before Homo heidelbergensis, before our species had the physical capacity for the kind of complex language that allows you to understand this sentence. Whatever Andromeda looks like right now, whatever is happening in its core at this moment, whatever supernovae have detonated, whatever has changed at its edges, whatever clouds of gas have collapsed into new stars, you will not see it for 2.537 million years. Your children will not see it. The civilization that succeeds your civilization, if there is one, will probably not see it. No human being who shares biological ancestry with any person alive today will live to see the light that is currently leaving Andromeda. But that is the nearest large galaxy. Go further. The Virgo cluster of galaxies sits approximately 53.8 million light-years away, May et al. 2007. What you see when you look at it, assuming access to a telescope capable of resolving individual galaxies within it, is those galaxies as they existed 53.8 million years ago. The Eocene epoch. Whales were four-legged land mammals returning to the sea. Primates existed in early forms, but nothing that would recognize itself in a mirror in the way modern humans do. The continents were in different positions. The atmosphere had a different composition. The planet was warmer, the poles ice-free, the oceans occupied by creatures that no longer exist. That is the era whose light is only now reaching your instruments. Go further still. The Coma cluster, 321 million light-years. The Great Wall of Galaxies, approximately 200 to 300 million light-years in depth, Geller and Huckra 1989. The observable universe, the full sphere of spacetime we can in principle detect with any instrument, extends 46.5 billion light-years in every direction, Planck Collaboration 2020. At the edge of that sphere is the cosmic microwave background, the faint thermal radiation left over from the universe's infancy, 380,000 years after the Big Bang. That is what we see at the outermost boundary of the observable universe. Not galaxies, not stars, not anything that has existed for 13.4 billion years. A wall of ancient light from a time before any coherent structure in the universe had formed. We are surrounded, in every direction we point our instruments, by different eras of cosmic history, all arriving simultaneously at our detectors. Think carefully about what this means. The observable universe is not a snapshot of the universe as it currently exists. It is a layered archaeological record, a series of nested historical periods, each shell of observable space corresponding to a different moment in the past, all arriving at Earth at this precise instant. When astronomers say they are studying the early universe, they are not using a figure of speech or running a computer simulation. They are literally looking at light from 13 billion years ago, because the light from that period is only now, after 13 billion years of travel, reaching our instruments. The universe we study is the universe as it was. The universe as it is exists entirely beyond our perception. This is not a solvable problem. It is not a temporary technological limitation awaiting the next generation of telescopes. It is the universe telling you, in the precise and unambiguous language of physics, that you are a creature whose perception cannot reach the present moment of the cosmos you inhabit. You have spent your entire life looking at a photograph and believing it was a window. It was always a photograph. And the subject of that photograph, everything beyond your own atmosphere, has been moving, changing, dying, and being born in a present moment you will never access. This is what a light year actually means. The distance is real, the time is also real, and they are the same measurement, inseparable, permanent, without exception. The person who first proved that light travels at a finite, measurable speed. The person who cracked open the question that ultimately leads to everything you have just heard was not primarily a physicist. Ole Rømer was a Danish astronomer who, before he became famous for anything to do with light, spent significant portions of his career as an administrator. He was, in the practical day-to-day sense of the word, a man who managed things, organized things, made sure other people could do science properly. He served as royal mathematician to King Louis XIV of France and ran the administrative machinery of the Paris Observatory. The budgets, the schedules, the instrument maintenance, the grinding institutional labor that history books tend to compress into a single dismissive sentence before moving on to the discovery. He later organized the decimal system of weights and measures for Denmark, reformed the Danish calendar, and served as prefect of police in Copenhagen, where he reorganized the city's water supply and street lighting. He was an accountant of civilization. He also, quietly and systematically, changed humanity's understanding of the nature of light. He was born in 1644 in Aarhus, Denmark, the son of a merchant sailor. His path into science came through the astronomer Rasmus Bartholin, who employed the young Rømer after recognizing his aptitude for mathematics and observation. From Bartholin, he moved to Paris, to the observatory, to the telescopes and the data, and the long nights of watching the sky with the meticulous attention that 17th-century astronomy demanded. He kept records. He compared observations. He noticed patterns, and one of the patterns he noticed, in data that had been accumulating since Galileo's discovery of Jupiter's moons in 1610, was a discrepancy that nobody had satisfactorily explained. He died in 1710. In between birth and death, he did the thing that nobody had managed to do before him. He proved that light takes time to travel, not theoretically, not philosophically, measurably with a specific number attached. Before Rømer, this was not a settled question, and the history of failed attempts to settle it is worth dwelling on, because it illuminates how genuinely hard the problem was. Galileo Galilei had attempted to measure the speed of light in approximately 1638, using what sounds in retrospect like an appealingly direct method. He positioned himself on one hilltop with a lantern. A colleague stood on a distant hilltop with another lantern. The procedure: Galileo uncovers his lantern. His colleague, seeing the light, immediately uncovers his own. Galileo measures the time between uncovering his lantern and seeing the response light from his colleague. That round-trip time, divided by twice the distance between the hills, would give the speed of light. The experiment failed to produce a useful result, not because Galileo executed it poorly. The experiment was executed correctly. It failed because human reaction time, approximately 200 milliseconds, completely swamped any measurable delay caused by light traveling between hilltops a few kilometers apart. At the speed of light, crossing a few kilometers takes less than 20 microseconds. That is 10,000 times shorter than the blink of a human eye, 10,000 times too brief to measure with any technology available in 1638. Galileo concluded that if light had a finite speed, it was extraordinarily rapid, a conclusion simultaneously correct and scientifically useless. René Descartes, working from philosophical premises rather than experimental ones, argued that the speed of light was not merely rapid but instantaneous, infinite. He built this into his system of physics as a requirement. If light were not instantaneous, he reasoned, certain astronomical observations would show measurable anomalies. He was working backwards from an assumed conclusion, and the methodology was fundamentally flawed. But Descartes was enormously influential, and his assertion that light traveled instantaneously was not easy to dislodge from natural philosophy. Isaac Beeckman had proposed experiments similar to Galileo's. Robert Hooke had speculated that light, if it had a finite speed, moved so fast as to be effectively instantaneous on any measurable scale. Francis Bacon, more cautiously, had suggested the question was genuinely open. None of them had measured anything. The question stood open, waiting for data. Rømer closed it, and he did so not by pointing instruments at lanterns on hilltops, but by watching the moons of Jupiter for years. The specific moon is Io, the innermost of the 4 large Galilean moons that Galileo had discovered in 1610. Io orbits Jupiter in approximately 42.5 hours, a quick, regular orbit whose timing could be measured precisely using the telescopes available in the 1660s and 1670s. From Earth, the geometry of Io's orbit is such that it regularly disappears behind Jupiter and then reappears on the other side. These eclipses are geometrically predictable. Given the size of Io's orbit and its period, Keplerian mechanics allows calculation of exactly when it should disappear and reappear, years into the future. For most of the year, the predictions hold. Io appears and disappears almost exactly when the mathematics says it should. The timing is so reliable that 17th century astronomers were using Io's eclipses as a navigational tool, a cosmic clock visible from anywhere on Earth, theoretically capable of allowing sailors to determine their longitude by comparing the observed eclipse time to a table of predicted times for a reference meridian. But not at all times of year. When Earth is on the far side of its orbit from Jupiter, when the geometry of the solar system has placed Earth at its maximum distance from the gas giant, roughly 1 astronomical unit farther away than when they are closest, Io's eclipses arrive late. Not randomly late. Systematically, consistently, measurably late, with the delay increasing as Earth moved to maximum distance and decreasing as Earth moved closer. The maximum observed delay, relative to the mathematically predicted time, was approximately 22 minutes, and the pattern repeated precisely every year as Earth made its circuit around the Sun. Giovanni Cassini, the director of the Paris Observatory and Rømer's superior, had noticed the same pattern in 1675, 1 year before Rømer's announcement. Cassini briefly considered the same explanation that Rømer would later champion, that the delay was caused by light taking longer to travel the greater distance between Earth and Jupiter when Earth was on the far side of its orbit. He published a note to this effect, raising it as a possibility. Then he backed away from it. The idea troubled him. The mathematics of it required the speed of light to be a specific, finite number, which felt philosophically uncomfortable, and which the imprecision of the available data made defensible to dispute. The pattern could, Cassini argued, be due to unknown irregularities in Io's orbit rather than anything having to do with light. He returned to the orthodox position. The discrepancy was an anomaly, not yet fully explained, awaiting better data. This is the decision point that separates Cassini from Rømer in the historical record. One man looked at the same pattern and flinched. The other held still. Rømer, working with the same data, accumulated over years of systematic observation at the Paris Observatory, including 140 observed eclipses of Io, Tuber 2004, arrived at the explanation and did not abandon it. The 22-minute discrepancy, he argued, was caused by the finite speed of light crossing the additional distance between Earth and Jupiter when Earth was at its farthest point in its orbit. The extra distance was approximately the diameter of Earth's orbit, what we now call 2 astronomical units, roughly 300 million kilometers. Light crossing 300 million additional kilometers took approximately 22 minutes. Therefore, the speed of light was the distance divided by the time, approximately 220,000 kilometers per second. This number is wrong. The correct value is 299,792 kilometers per second. Rømer's estimate was off by about 26%. The error came from an inaccurate measurement of the astronomical unit, the Earth-Sun distance, which in 1676 had not been precisely determined. Rømer's method was entirely correct. His data was genuine. His logic was impeccable. The absolute number he produced was inaccurate through no fault of his own, because it depended on a measurement, the size of Earth's orbit, that nobody had yet nailed down. In September 1676, Rømer did something that required a specific kind of confidence. He made a falsifiable prediction. He announced, publicly and in advance, that the eclipse of Io scheduled for November 9th of that year would arrive approximately 10 minutes later than the standard orbital model predicted. He stated this prediction in a letter read to the French Royal Academy of Sciences on November 21, 1676, after the eclipse had already occurred and been observed. But crucially, the prediction had been on record before the observation. The eclipse had arrived late, approximately 10 minutes late, consistent with Rømer's prediction. The Academy was not swept away. The reception was skeptical, restrained, and in the case of Cassini, openly dismissive. Cassini, who held the institutional authority of the observatory directorship and the accumulated credibility of decades of careful work, publicly questioned Rømer's interpretation. The irregularities in Io's orbit, Cassini maintained, had not been adequately ruled out as an alternative explanation. The finite speed hypothesis remained, in the Academy's view, an interesting conjecture rather than an established fact. Rømer returned to Denmark in 1681. He took up a professorship at the University of Copenhagen. He built instruments. He made more observations. He organized, administered, reformed, policed, because he was, fundamentally, a man who managed things, and science was one of the things he managed. He constructed what was, at the time of its completion in 1704, one of the most precise transit instruments in Europe, housed at his private observatory at Tusculanum outside Copenhagen. He accumulated more data. He never stopped working. But in 1728, 18 years after his death, the vindication arrived. The English astronomer James Bradley had been attempting to measure stellar parallax, the tiny apparent shift in the position of nearby stars caused by Earth's movement around its orbit, using the star Gamma Draconis. He did not find what he was looking for. Instead, he found something else, a systematic shift in stellar positions that followed a pattern related to Earth's orbital velocity, not its orbital position. Stars appeared to shift in a way that corresponded not to where Earth was in its orbit, but to which direction Earth was moving. Bradley worked out the explanation over the course of 1728, and it was one of the great moments in the history of physics: stellar aberration. When you are moving through space, light appears to come from a slightly different direction than its true source, just as rain that is actually falling straight down appears to fall toward you when you are running through it. The angle of aberration depends on the ratio of Earth's velocity to the speed of light. Bradley measured that angle, 20.5 arcseconds, Bradley 1728, and from it calculated the speed of light. His result, approximately 301,000 kilometers per second. His method was completely independent of Rømer's. He did not use Jupiter's moons. He did not rely on eclipse timing. He used stellar positions measured with a zenith sector mounted in his rented house in Kew, England, watching Gamma Draconis through a chimney-width gap in the roof, logging the star's position night after night through the changing seasons. The precision required was extraordinary. He was measuring angular displacements of arcseconds in an era before any systematic understanding of atmospheric refraction, before temperature-compensating instruments, in a country famous for its cloud cover. He succeeded. Two independent methods, using completely different phenomena, eclipse timing and stellar aberration, produced consistent results. Both said, the speed of light is finite. Both said, Rømer was right. Rømer's grave could not receive the news. The history of the measurement did not stop with Bradley. Every generation refined the number. In 1849, the French physicist Hippolyte Fizeau made the first purely terrestrial measurement, using a rotating cogwheel and a mirror placed 8,633 meters away. Light was fired through a gap in the cogwheel's teeth, traveled to the mirror, bounced back, and was either blocked by the next tooth or passed through the following gap, depending on the wheel's rotation speed. Fizeau timed the wheel's rotation at which the returning light was precisely blocked and calculated the round-trip travel time. His result, approximately 313,300 kilometers per second, within 5% of the true value, without any reference to astronomical observation. Léon Foucault refined the method in 1862 using a rotating mirror rather than a cog-wheel, eliminating certain sources of error, and produced 298,000 kilometers per second, within 0.6% of the correct value. Albert Michelson took up the measurement as a near-lifelong obsession beginning in 1877, refining his apparatus across 5 decades, eventually deploying in 1926 a rotating octagonal mirror in a precisely measured baseline on Mount Wilson in California. His 1926 result, 299,796 kilometers per second, Michelson 1927, within 4 kilometers per second of the modern defined value. In 1983, the General Conference on Weights and Measures redefined the meter. Rather than measuring the speed of light in independently defined units of distance and time, the scientific community set the speed of light as exact, 299,792,458 meters per second, by definition. The meter became a derived unit, defined as the distance light travels in 129979245 of a second. The speed of light is now not a measured quantity carrying some associated measurement uncertainty. It is a definition, a fixed point, the bedrock on which an entire system of measurement rests. This is not a bureaucratic technicality, and it is not arbitrary. It reflects something deep and important about the structure of physics. The speed of light is not a property of light in particular. It is a property of spacetime itself. It is the speed at which causation propagates, the rate at which effects can travel from causes, the maximum velocity at which any signal, any particle, any form of information transfer can move through the fabric of the universe. Light travels at this speed because photons are massless. Any massless particle travels at exactly c, but c itself exists independently of light. It is the geometry's own speed limit, built into the structure of spacetime at a level more fundamental than any particular particle or wave. And that limit, that absolute geometry-level constraint, is what transforms a light year from a large distance into a temporal fact. When you look at something 100 light-years away, you are not receiving information from a point in space that is 100 light-years distant. You are receiving information from a point in spacetime that is 100 light-years in space and 100 years in the past. The distance and the time are not two separate measurements that happen to have the same numerical value. They are the same fact expressed in two different units. Light year and year are different names for the same quantity, looked at from two directions. Rømer proved that light takes time to travel. Fizeau measured how much time. Michelson refined that measurement to 4 decimal places. The 1983 redefinition fixed the number into the bedrock of the measurement system. None of them could have known, or perhaps Rømer, staring at his data in the Paris Observatory in 1676, glimpsed the edge of it, that the number they were so carefully measuring was a door. That behind it waited a reconstruction of what observation means, what distance means, what now means. That the finite speed of causation would eventually force the conclusion that the present state of the universe is not merely unknown, but permanently, structurally inaccessible to any observer within it. He measured a number. The number had a door behind it. We have been walking through it ever since. It is worth pausing on what Rømer's work cost him personally. He spent years defending an interpretation that the most powerful astronomer in Europe publicly questioned. He returned to his home country without vindication. He built more instruments, made more observations, continued working, and died without seeing the independent confirmation that would silence all doubters. The posthumous vindication arrived not as a correction to a grave injustice, but as a quiet addition to a scientific record that had already moved on. This is the ordinary texture of scientific progress. A person sees something true, says it clearly, is doubted, continues working, dies, and is later confirmed by someone who did not know them. The universe does not adjust its timelines to suit human careers. The speed of light was what it was before Rømer measured it, and after he died, and will remain what it is after every instrument that has ever confirmed it has crumbled into dust. The measurement outlasted the measurer, as measurements do, as all true things do. Before the first analogy begins, a precise statement of what is being explained. Light travels at 299,792,458 meters per second. This is fast, so fast that light circles the Earth 7.5 times in 1 second, crosses the Moon's distance in 1.3 seconds, crosses the Sun's distance in 8 minutes and 20 seconds. It is also, at cosmic distances, catastrophically, existentially slow. The result of this combination, very fast by any human standard, impossibly slow by cosmic ones, is that every observation we have ever made of the universe is an observation of the past, not the recent past close enough to approximate as present. A past that ranges, depending on what you are looking at, from nanoseconds to 13.8 billion years. This creates a condition that has no name in everyday language, because everyday language was developed by creatures who evolved within a thin shell of atmosphere on a single planet, whose entire lived experience occurs within distances so small that the travel time of light across them is biologically imperceptible. We have a perfectly good word for far away. We do not have a word for far away in space, and therefore also far away in time, with those two facts being the same fact, expressed in different units, inseparable at any level of analysis, without exception across the entire observable universe. We need 3 analogies to construct that understanding from scratch, the way a surgeon needs 3 different instruments to do what one cannot do alone. Each analogy is true, each is also incomplete. Together, they triangulate the reality. Imagine you receive a letter. It was mailed from Tokyo. You are in London. Standard international mail takes approximately 10 days. The letter contains news. My father passed away yesterday, it reads. We are planning the funeral for next week. You receive this letter 10 days after it was written. The father died 11 days ago. The funeral is either happening today or has already happened. Nothing in the letter is current. Nothing it describes is now. The letter is a historical document, a snapshot of someone else's reality as it existed 10 days in the past, delivered to you in the form of words on paper, arriving at your present moment from their past moment. You know this. You compensate for it automatically. If you write a reply, you write knowing that the funeral is already over, that your condolences arrive after the fact, that the situation the letter describes has already evolved in ways the letter cannot show you. The delay is built into the medium. Letters are not windows. They are time capsules sent voluntarily from one moment to another. Now change the medium. Replace the letter with light. Light is the postal system of the universe. It is the only carrier of information across space. When any event occurs anywhere in the cosmos, a star detonating in a supernova, 2 galaxies beginning to collide, a rocky planet condensing from a disk of gas and dust around a young star, the information about that event begins propagating outward in every direction at 299,792,458 meters per second. There is no faster carrier. There is no express option, no priority mail, no digital transmission that skips the physical medium. Every piece of information about every event in the entire observable universe travels by the same carrier, at the same fixed speed. And the distances mean that delivery times are not 10 days. They are thousands of years, millions of years, billions of years. When astronomers detected the supernova designated SN 1987A in the Large Magellanic Cloud on February 23, 1987, the brightest supernova visible from Earth since Kepler's supernova of 1604, they were receiving a letter that had been traveling for 168,000 years, Panagia 1999. The star that exploded, Sanjalik degrees 202, detonated 168,000 years ago. In the Middle Paleolithic period of Earth's prehistory, when Homo sapiens were behaviorally archaic, anatomically transitional, distributed in small populations across Africa and possibly parts of Western Asia, when Neanderthals occupied Europe, when modern human cognition, as we currently define it, had not yet fully emerged. The letter from that star's death had been in transit for 168,000 years. Astronomers discovered the explosion on a February morning in 1987. The explosion had already been over for 168 millennia. Now here is where the letter analogy must be stretched to show what makes astronomical observation fundamentally stranger than receiving delayed mail. With the letter from Tokyo, you know the delay. You know when it was sent. You can calculate when the described events occurred relative to today. And crucially, you can call Tokyo. You can send a message back. You can receive updated information via a channel faster than the original letter, email, a phone call, a video feed, and learn what has happened since the letter was written. With astronomical observation, there is no phone call. There is no faster channel. There is only the light. There is no way to contact Sanjalik degrees 202 and ask how things are now. There is no signal that could reach it in less than 168,000 years, because no signal travels faster than light. Any message we sent in the direction of the Large Magellanic Cloud today would arrive there in 168,000 years. Any response to that message would take another 168,000 years to return. We are in a one-way correspondence with the universe, receiving letters from the past with no ability to request updates. The most recent information we can ever have about any astronomical object is the light currently arriving from it. And that light is always, exactly, as old as the object's distance in light years. The universe sends letters. We receive them. The post office is physics itself, and it runs on exactly one schedule, 299,792,458 meters per second, no exceptions. This is the first layer. The delay is real. The channel is one-directional. The present state of every distant object is, in the strictest sense, unreachable correspondence. But the letter analogy still implies something that is not quite right. Letters are sent deliberately, by agents with intentions, describing specific events. Light from stars is not sent deliberately. It is emitted continuously, in all directions, without choosing a recipient or describing a particular moment. The light arriving at your eye from Andromeda right now is not a message about one specific event. It is the accumulated emission of 2.537 million years of photons, all of which left Andromeda at different times, all of which happened to be aimed in exactly the right direction to cross 2.537 million light-years of space and arrive at your retina in this particular moment. The light is not a letter. It is something older and stranger. For that, we need the second analogy. You are looking at a photograph. The photograph shows a house. The house is on fire. The photograph was taken 5 minutes ago. You are looking at it now. Is the house still burning? You cannot know. The photograph does not tell you. It shows you the house as it was at the moment of capture, the flames, the smoke, the structure holding or beginning to fail. 5 minutes have passed since that moment. In 5 minutes, the fire could have been extinguished, the roof could have collapsed, the structure could have burned to its foundation, or the fire department could have arrived and contained the blaze to one room. The photograph is a record of a past moment. It contains no information about any subsequent moment. The gap between the photograph's moment and your present moment is, from the photograph's perspective, an information void. You understand this intuitively. The photograph is clearly a historical document. Nobody looks at a photograph of a burning house and believes they are watching the fire in real time. Now take a telescope and point it at the Andromeda galaxy. What you see is a photograph, not a physical photograph with silver halide grains or digital pixels, but a photograph in the most precise physical sense, a record of light that was emitted at a specific time in the past and captured by your instrument or eye in the present. The image of Andromeda that forms in your eyepiece is a record of Andromeda as it was 2.537 million years ago. Every photon that constitutes that image left Andromeda 2.537 million years ago. The image is 2.537 million years old. It is a photograph. Is the house still burning? Is Andromeda still there? Almost certainly yes. We know from stellar dynamics and galactic evolution that galaxies on Andromeda's scale survive for billions of years, and 2.537 million years is not long enough for dramatic structural change. But almost certainly, and we know from models of evolution, are different from direct observation. The current state of Andromeda is not something we can verify. It is something we must infer. The present Andromeda exists. We have no access to it. Now extend this to the distances, where the photograph analogy becomes genuinely alarming. Consider what we see when we look at the most distant observable galaxies. Objects 10, 11, 12 billion light-years away. We see small, irregular, intensely star-forming objects that look nothing like the large, structured, relatively quiescent spiral galaxies we see nearby. We know from our models of galactic evolution that those early, chaotic objects eventually developed into the structured galaxies we see in the more recent universe. The photograph of those early galaxies shows the house before the remodel, before decades of construction, renovation, and change turned the structure into something unrecognizable to the person who last saw it in its original form. The early galaxies we observe at 12 billion light-years are not early galaxies, in the sense that they are young and will someday grow up. They grew up 12 billion years ago. They grew up while their light was in transit. The photograph we have is of an embryo. The adult form has been living, evolving, changing, and potentially dying for 12 billion years, and we have not seen any of it, because the light showing us those 12 billion years of change is still in transit. It will arrive over the next 12 billion years, in sequence, each year's light slightly more recent than the last. We are receiving the early chapters of stories whose endings happened before multicellular life appeared on Earth. But there is one more dimension to the photograph analogy that must be stated explicitly, because it is the element that transforms interesting limitation into something that deserves the word dread. We have named these photographs. We have cataloged them. We have given them designations, NGC numbers, Messier numbers, names chosen by the astronomers who first captured their image. We have built taxonomies, classification systems, databases. We have organized our photographs into a map of the universe, and we study that map as if it were a representation of a place. It is a representation of multiple times, simultaneously disguised as a place. Every catalog of deep sky objects is a catalog of historical moments, each measured in light years from Earth, each therefore measured in years into the past. The map of the universe is not a map of space. It is a map of space-time, of space crossed with history, compressed by the convention of ignoring the temporal axis and presenting only the spatial one. The galaxies we have named exist. Their light has arrived, but the entities we have named at those distances in those photographic records, many of them have changed beyond recognition. Some no longer exist in the forms we cataloged, and we have no way of knowing which ones. We have named things that may no longer be. This is not speculation. This is the logical consequence of finite light speed applied to objects that evolve on timescales shorter than their distance in light years. Any galaxy more than a few 100 million light years away may have changed dramatically, merged, distorted, quenched its star formation, in the time its cataloged image has been in transit. The name we gave to a photograph is not necessarily the name of something that currently exists in the form the photograph shows. We have always been studying ghosts and calling them present. This is the most structurally complete analogy, and it requires the most careful construction. Take the time to build the image precisely. You are standing at the center of a perfectly transparent sphere. You can see in every direction simultaneously. The sphere extends outward from you in all directions without boundary. Now imagine that every distance from you corresponds to a time in the past. Objects 1 light year from you in this sphere are visible to you as they were 1 year ago. Objects 100 light years away are visible as they were 100 years ago. Objects 1,000 light years away, 1,000 years ago. 10,000 light years, 10,000 years ago. 100,000 light years, 100,000 years ago. This is not a model or a metaphor or a simplification. This is the literal geometric structure of observation in a universe with a finite speed of light. Every point in space that you can observe is also a point in time, a point in the past, separated from your present moment by exactly the light travel time from that point to you. The sphere of space you observe is simultaneously a sphere of history. Now, look in any direction. The stars nearest to you in that direction are visible as they were a few years to a few thousand years ago. The stars at the edge of our galaxy, 26,000 light years from Earth in the direction of the galactic center, are visible as they were 26,000 years ago, in the Upper Paleolithic, when Homo sapiens were still primarily hunter-gatherers, when the oldest cave paintings were being made in France and Spain, when mammoths still walked the Eurasian steppe. Look further. The nearest large galaxy, Andromeda, 2.537 million years ago. The Virgo cluster, 53.8 million years ago. The most distant individually observed galaxy at the time of this script's research, GS 9209, approximately 25 billion light years in terms of current proper distance. Carnell et al. 2023, billions of years into the universe's past. And at the very edge of the observable sphere, at the outermost boundary of what any instrument can in principle detect, sits the cosmic microwave background, CMB. The thermal radiation released 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen for the first time. The CMB is the wall at the edge of the observable universe, not a wall in space, but a wall in time. It is the furthest we can see, not because space ends there, but because before that moment the universe was opaque, an ionized plasma through which light could not travel freely. The sphere of observation you inhabit extends from nanoseconds in the past at its center to 13.8 billion years in the past at its surface. You are surrounded, in all 4 pi steradians of solid angle, by different eras of cosmic history. Now comes the aspect of this analogy that deserves to be repeated slowly, because it contains the deepest strangeness. Every other observer, anywhere in the universe, is sitting at the center of their own sphere. Their sphere is not your sphere. Its center is a different location. The distances from that center to any given object are different from yours. Therefore, the historical eras visible from that center are different from yours. If there is a civilization on a planet orbiting a star in the Andromeda galaxy, present tense, in this moment, that civilization is looking out at a universe that includes Earth in its sphere of observation. But the Earth they can see is the Earth as it was 2.537 million years ago. They cannot see us. They cannot see our cities, our satellites, our electromagnetic leakage, our civilization. They can see, If their instruments are powerful enough, the planet Earth as it existed 2.537 million years before any of this. Our current moment is beyond their observable sphere. The light carrying information about our civilization has not yet reached them. Meanwhile, we are looking at Andromeda as it was 2.537 million years ago. We cannot see what they are doing now. We cannot see whether they exist. We see a galaxy from a time before their star may have even formed, depending on how old their star is. Neither civilization can observe the other's present. Both are permanently confined to observing each other's past. There is no cosmic present. There is no moment that all observers share. Every observer is at the center of their own historical sphere, and no two spheres in the universe, separated by any non-zero distance, contain the same slice of time. The universe does not have a now that any observer can access. It has a series of nested local presents, each bounded by a horizon of historical observation, each separated from every other local present by exactly the light travel time between them. Physicists call this the relativity of simultaneity, and they have a more technical apparatus for describing it. But the phenomenological experience of it is this. The present moment you are experiencing, this moment, right now, does not exist as a now for any observer more than a few light seconds away. For them, your now is either still in their future or already in their past, depending on the geometry of your motion relative to theirs. The present is local. It does not scale. It does not extend across the universe. It is a thin shell around each observer, beyond which the universe is history in all directions. The specific structure physicists use to describe this is the past light cone, the full set of events in spacetime from which light has had time to reach a given observer at a given moment. Everything inside your past light cone is observable to you. It is the set of events that could have sent you information by now. Everything outside your past light cone, including the current moment of every object more than zero distance from you, is beyond your observational reach. Not because of technological limitations, because the information from those events has not arrived yet and cannot arrive faster than light. The past light cone is not a limitation of instruments. It is a boundary written into the geometry of spacetime. The present state of the universe, not your city, not your planet, not your solar system, but the actual universe, the full structure of it, all of it simultaneously, right now, lies entirely outside every observer's past light cone. The present universe is not observable from within the universe. It is the one thing that no observer, anywhere, at any level of technological sophistication, can directly perceive. We are each sitting at the center of a sphere of history, calling it the universe. It is the universe, but it is not the present universe. It is the past universe, delivered to us continuously at the speed of light from every direction simultaneously. The core insight, stated once more because it must be stated more than once. A light year is not just a distance. It is a temporal displacement. It is how far into the past you are looking when you observe something at that distance. The observable universe is not a three-dimensional snapshot of a place. It is a four-dimensional archive of different historical eras, arranged by distance and therefore by age, all arriving at your instruments simultaneously. The present state of that universe is permanently beyond your reach, not because your instruments are insufficiently powerful, but because the information from the present has not yet arrived and will not arrive until it is itself historical. We are consciousness sitting inside an archive, convinced we are watching the world. The archive goes back 13.8 billion years. No page of it describes today. When most people encounter the idea that we observe the past rather than the present, their minds immediately search for exits. There is an instinctive resistance, a set of objections that feel not just reasonable but necessary, that arrive within seconds of confronting the idea, before the conscious mind has fully processed what is being said. These objections are not foolish. They are the natural responses of minds shaped by evolution to navigate a world where distance and time are experientially separable, where far away means spatially distant, and where the distinction between observation and reality has never caused any practical problem. Each objection contains a flaw. Each exit, examined carefully, is sealed. The purpose of this act is to walk through each one slowly and close it. Escape Route 1. We can calculate where things are now. This is the first and most seductive refuge, because it is partially true. We calculate planetary positions with extraordinary precision. Orbital mechanics allows us to predict where Mars will be on any given date years or decades in advance, and spacecraft navigators rely on those calculations to design missions that arrive at the correct point in space after years of travel. We can calculate where Jupiter's moons will be and when Io's eclipses will occur, which is precisely what made Rømer's observation possible. Calculation extends human knowledge beyond direct observation. So why not simply calculate where distant astronomical objects currently are, rather than being troubled by where we see them? The answer has two layers, and both must be examined. The first layer is practical. Any calculation of a distant object's current position requires knowing its position and velocity at some reference time. That reference time is the moment of observation, meaning the moment when light from the object reached our instruments. That light is old. The position and velocity we measure are the position and velocity of the object as it was when that light was emitted. For an object 10 million light-years away, we are extrapolating forward from conditions that existed 10 million years ago, using a velocity measured 10 million years ago. Through 10 million years of time during which the object has been subject to gravitational influences, mergers, interactions with neighboring objects, and the large-scale effects of cosmic expansion. For nearby solar system objects, this extrapolation is reliable because the timescales involved are short enough that our models of the physics governing those objects are accurate. For distant galaxies, we are projecting forward from a starting point that is 10 or 100 or 1,000 million years stale. The uncertainty compounds. The result is not a measurement of where the object is. It is a model output, the output of our best theoretical framework applied to ancient data. Useful, but not the same as observation. The second layer closes the exit permanently. Even if we could calculate exactly where a distant object is right now with perfect accuracy, we cannot confirm the calculation. The calculated current state is an inference. It remains unconfirmable for exactly as long as the object's distance in light years. If we want to confirm our calculation of what a galaxy 100 million light-years away is doing right now, we must wait 100 million years for the light that is currently leaving it to arrive. By that time, our civilization will be something we cannot imagine from here. The calculation gives us a model of the present. It does not give us access to the present. A model of the present and the present itself are not the same thing. The universe does not accept models as substitutes for observations. The gap between what we can calculate and what we can verify is filled entirely by time, light travel time, and it cannot be collapsed by any cleverness of mathematics. Escape Route 2. The delays are negligible for practical astronomy. This objection reframes the problem as a matter of practical significance rather than fundamental structure. Yes, we observe the past, but astronomers know this, account for it in their work, and produce reliable science anyway. Cosmology, galactic dynamics, stellar astrophysics, all of it proceeds successfully using historical data. The fact that we observe the past does not prevent us from understanding the universe. So perhaps the correct response to all this is not dread but simple professional acknowledgement. We observe the past, we correct for it where necessary, we continue. This response confuses scientific utility with metaphysical completeness. The fact that astronomy can do useful work using historical data does not mean the universe has given us access to the present. It means that useful science can be done using historical data. Both things are true simultaneously. The scientific utility of historical observation and the structural inaccessibility of the present are not in tension. They coexist. But something is being passed over in the "it doesn't practically matter" response, and it is important. The things that have changed in the universe during the transit time of the light we observe are not necessarily things we have good models for. We model galactic evolution using empirical data drawn from observations at different distances, meaning different times. We see early galaxies at 12 billion light-years, intermediate galaxies at 5 billion, recent galaxies at 1 billion, nearby galaxies as they appear today, and we assume that the sequence tells us how galaxies evolve over time. This is a reasonable and productive assumption, but it means our understanding of the present state of any given galaxy is not derived from observing that galaxy in the present. It is derived from observing other galaxies at other times and assuming that this galaxy followed a similar developmental path. This is archaeology, not surveillance. We are reconstructing the present from historical samples of analogous objects. The reconstruction is powerful. It is not observation. And then there is the simpler, more uncomfortable fact. The specific objects we have named, cataloged, and claimed to know, the specific galaxies in our deep field surveys, the specific quasars in our databases, the specific clusters we have measured and mapped, many of them have changed in the time their light has been traveling to us. Some no longer exist in their observed form. Some have merged. Some have had their star formation quenched, their active nuclei stilled, their structure disrupted by gravitational interaction. We catalog photographs of things that have been evolving for millions or billions of years since the photograph was taken, and we use those catalogs as if they describe the current inventory of the universe. They describe the historical inventory of the universe. The practical irrelevance of this for Tuesday morning calculations does not dissolve the fact of it. The map of the universe is a map of the universe's past. It is a very good map. It is not a map of now. Escape Route 3. Quantum mechanics provides a loophole. This exit comes in several versions, the most common being quantum entanglement and, separately, the expansion of space. Quantum entanglement is real and experimentally confirmed to a level of precision that eliminates doubt. When two particles are entangled, measuring one instantaneously determines the state of the other, regardless of the distance between them. In experiments conducted over distances of more than 1,200 kilometers, including satellite-based entanglement experiments conducted by Pan et al. 2017, the correlations appear with no measurable delay. They are genuinely, in some sense, instantaneous. Einstein called this spooky action at a distance in a letter to Max Born in 1947, and he found it profoundly troubling for reasons related to the structure of relativity. The correlations are real, they are instantaneous, and they cannot be used to transmit information faster than light. This is not a technological limitation. It is fundamental to how entanglement works. When you measure your entangled particle, you get a random result. You have no control over what result you get. When your colleague measures their entangled particle, they also get a random result. The results are correlated. They will match in a way that could not have been prearranged classically. But the correlation can only be verified by comparing the two results, which requires a classical communication channel that travels at or below the speed of light. The entanglement itself carries no information. There is no signal. There is no mechanism by which one observer can use their particle to send a message to the other observer. You cannot use entanglement to transmit data because you cannot choose what measurement result you get. No information about the present state of any distant object travels via quantum entanglement. No signal of any kind exceeds the speed of light. The no-communication theorem in quantum mechanics is not a conjecture. It is a proved result, derived from the basic axioms of the theory, Girardi, Rimini and Weber 1980. The expansion of space presents a different version of the loophole. Distant regions of the universe are receding from us at velocities that exceed the speed of light due to the expansion of spacetime itself. The recession velocity of objects beyond the Hubble radius, approximately 14.2 billion light-years, Davis and Lineweaver 2004, exceeds c. Is this faster-than-light travel? Does it create a channel for superluminal information transfer? No, the expansion of space does not carry objects through space faster than light. It expands the space between objects, increasing the distance without any local velocity exceeding c. No signal passes through any point in spacetime faster than 299,792,458 meters per second. The expansion of space does not create a superluminal channel. It does the opposite. It removes portions of the universe from our observable sphere, expanding the region of the cosmos from which we can never receive information. Every year, the volume of the universe that is permanently beyond our observational reach grows. The observable universe is shrinking relative to the total universe, and the expansion of space is the reason. The quantum loophole does not exist. The expansion loophole is a misunderstanding. The speed limit holds everywhere, for everything, always. Escape route 4. This only applies to very distant things. This is the most psychologically comfortable exit, and it contains the most truth. At human scales, across a room, across a city, even across the planet, the time it takes light to travel is so small that the delay is biologically and practically imperceptible. A nanosecond is not a meaningful unit for everyday experience. The fraction of a millisecond it takes a signal to bounce off a satellite is not something that affects how we interact with the world. The delays are real and measurable in laboratory conditions, but they are, for all ordinary purposes, zero. But practically zero and zero are different, and the mechanism that produces a nanosecond delay across a room produces a 2.537 million-year delay across the Andromeda galaxy. The physics is identical. The scale differs. The principle does not. There is also something this escape route refuses to complete. Even at human scales, you have never perceived the present of anything. The light from every object you have ever looked at has been in transit for some duration, always a positive duration, never zero before it reached your eye. For your coffee cup, that duration is a fraction of a nanosecond. For the moon you looked at last night, it was 1.3 seconds. For the star you wished on as a child, it was years or decades or centuries, depending on which star. You have never, in your entire life, perceived the present moment of anything except the electrochemical states of your own nervous system, and even those are subject to internal processing delays of hundreds of milliseconds between event and conscious experience. The present is not accessible even to your own perception, not fully, not precisely. You are always slightly behind. At the scale of your body, this is harmless. At the scale of the room, it is imperceptible. At the scale of the cosmos, it is the central organizing fact of all observational science. Escape route 5. Future technology will solve this. This is the most forward-looking refuge. Perhaps some future physics, currently unknown, will reveal a mechanism that allows information to travel faster than light, or that gives observers access to the present state of distant objects through some means we have not yet discovered. This cannot be ruled out with absolute certainty, because physics has surprised us before and may surprise us again. But the evidence against it is not merely the absence of faster-than-light communication technology. It is that faster-than-light information transfer is prohibited by the structure of special relativity, which has been confirmed to extraordinary precision across more than a century of experimental tests, spanning an enormous range of energies, velocities, and conditions. Any future physics that allows faster-than-light information transfer would require not a modification of special relativity, but its replacement. a new foundational framework for spacetime in which the causal structure we have measured and confirmed is an approximation or a special case. This is not impossible, but it is not a reasonable basis for comfort. We do not dismiss the implications of evolution because future biology might discover that Darwin was wrong about something. We do not dismiss germ theory because future medicine might find exceptions. The confirmation of special relativity's predictions, including the finite and absolute speed of information propagation, is among the most rigorous confirmation of any scientific framework that exists. Hoping it turns out to be fundamentally wrong in a specific and convenient way is not an exit. It is a wish. What remains when the routes are closed? All 5 exits are sealed. Let the inventory of what remains be stated plainly. The present state of the universe, the state of the cosmos right now, everywhere simultaneously in this moment, is not accessible to any observer within it. Every observation is historical. Every photograph of deep space is a record of a past that ranges from millions to billions of years old. Every name we have given to a distant galaxy is a name given to a historical object. Every map of the large-scale structure of the universe is a map of the universe as it was across a range of historical periods, compressed into a single image by the practice of ignoring the temporal axis. We have been studying the universe for as long as we have had instruments. We have accumulated an archive of extraordinary depth and precision. That archive is genuinely illuminating. The science built on it is genuinely reliable within its domain. The domain of that science is the past. The present universe, the one that exists in the same moment you are breathing, in the same moment these words are forming in your perception, is not in the archive. It is not in any instrument. It is not accessible by any method currently known or theoretically permitted by the laws of physics as we understand them. The universe is not silent because it has nothing to say. It is silent because its current messages have not arrived yet. They are coming. At 299,792,458 meters per second, from every direction, they are coming. The light that left Andromeda 1 second ago is 299,792 kilometers closer than it was a second ago. Every second, the present edges slightly less into the past. Every second, the ancient light recedes by another 299,792 kilometers toward us, which is to say, the light that is currently present in Andromeda will be our past in 2.537 million years. The present universe is approaching. It is always approaching. It will never arrive within our lifetimes, within our civilization's lifetimes, within any time frame that connects to anything we call us. The silence is not a failure of signal. It is a condition of physics. It is fixed. It is waiting. And it has always been waiting. Every civilization that has ever existed on this planet, every culture that developed a relationship with the night sky, that named the stars, that used them to navigate or to mark seasons or to tell stories about gods and ancestors, did so while looking at historical light and believing they were looking at the present sky. They were not wrong to look. They were not deluded. They were doing what observers inside a finite light-speed universe must do: work with the information that arrives, knowing or not knowing that what arrives is always the past. We know now. We have known technically since Rømer. What changes with knowing is not what we see. What changes is what we understand about what seeing means. The archive is still the archive. The present is still unreachable. The silence still holds. Knowing its name does not open any door. It only clarifies what kind of room we have always been standing in. Go back to the beginning. Right now, at this exact moment, you are looking at the past. This was the first sentence. You heard it some time ago at the start of this script, before the history, before the analogies, before the escape routes were closed one by one. It may have sounded at the start like a dramatic opening designed to create urgency before settling into something reassuring. Perhaps you were waiting for the part where it turned out that this was all manageable, a matter of perspective, a nuance that scientists account for without distress, a feature of physics that is interesting but ultimately leaves the world as it was before you sat down to listen. That part did not come. That part does not exist. What has changed since the opening is not the statement. What has changed is the full weight of what the statement means. When you look at the screen in front of you right now, the light it emits takes a fraction of a nanosecond, approximately 0.3 nanoseconds per centimeter of distance, to travel from its surface to your retina. You are seeing the screen as it was a fraction of a nanosecond ago. This is the smallest version of the truth. It is trivially small. It matters to no one. But it is real. The mechanism is operating even here at this scale in this moment. When you look at the moon on a clear night, full or crescent or new dark at the edge of daylight, you are seeing it as it was 1.266 seconds ago. The exact number depends on its position in its elliptical orbit. At perigee, approximately 1.19 seconds. At apogee, approximately 1.4 seconds. At the average distance of 384,400 kilometers, the delay is 1.282 seconds. In those 1.282 seconds, the moon has moved. Its shadows have shifted. Whatever process was occurring on its surface at the moment the light left, a micrometeorite impact, a dust avalanche on a crater wall, is now 1.282 seconds further along. The moon you see is not the moon. It is an image of the moon from 1.282 seconds in the past, currently crossing the 384,400 kilometers between there and your eye. When you look at the sun, which you should not do directly, but through a properly filtered telescope or during an eclipse, you are seeing it as it was 8 minutes and 20 seconds ago. The sunspot that appears in your filtered view, that structured magnetic region on the photosphere, it existed 8 minutes and 20 seconds ago. If it has since evolved, if a solar flare has erupted, if the spot has fragmented, if a coronal mass ejection has launched from its leading edge, you will not know for 8 minutes and 20 seconds after it happens. The light carrying that information is already traveling toward you. It will arrive on schedule. You will not be warned before it arrives. When you look at Proxima Centauri, the nearest star to the Sun, at 4.243 light-years, you are seeing it as it was 4.243 years ago. In that time, Proxima has continued its slow orbit of the Alpha Centauri binary system. If it flared, it is a red dwarf prone to violent flaring. The flare happened 4.243 years ago. The light from it is currently somewhere between Proxima and Earth, traveling toward us, due to arrive at some point in our future. We receive information about Proxima's flares years after they occur. And when you look at Andromeda, faint, extended, visible to the naked eye as a smudge in the constellation bearing the same name on a dark, moonless autumn night, you are looking at 2.537 million years ago. The full weight of that number, the light you see left Andromeda 2.537 million years before this moment. In that time on this planet, the entire genus Homo arose from Australopithecus ancestors, spread across the African continent and then beyond, developed increasingly sophisticated tools and language and symbolic thought, became anatomically modern, invented agriculture, writing, mathematics, astronomy, physics, and built the civilization in which a creature can sit in a room and understand, for the first time, what it is looking at when it looks at that smudge of ancient light. All of that, the entire human story, happened in the time since that light left its source. Andromeda does not know we exist. The light carrying news of our existence will not reach Andromeda for 2.537 million years. The sky above you, on any clear night anywhere on Earth, is an archive. Every point of light is a document. Every document is historical. The stars visible to the naked eye range from about 4 light-years away, Proxima Centauri, to about 2,600 light-years away, Deneb, if you are looking at it. Every photon from every one of those stars is a message from between 4 and 2,600 years ago. The stars you see tonight, the stars human beings have navigated by, named, and made into constellations across every culture in human history, you are not seeing them as they are. You are seeing them as they were. Some of them, the ones with the greatest distances, have already exhausted their nuclear fuel. Some are in the early stages of a terminal phase of evolution that will, in a few thousand years, end in supernova or planetary nebula. And you will not see it begin for thousands of years, because the light from its beginning has not yet crossed the gap. You have been navigating by corpses and not known it. Here is the shape of the universe you actually inhabit, stated in its complete form. You exist in the present. The universe also exists in the present, but the universe's present is not accessible to you. What is accessible to you is a sphere of historical information, extending 46.5 billion light-years in every direction, containing light from every era between 380,000 years after the Big Bang and approximately now. The inner edge of that sphere, the light that left its sources most recently, is not now. It is whatever moment corresponds to the distance of the nearest object you observe. For an object a light year away, it is a year ago. For your eyes looking at your hand, it is nanoseconds ago. There is no observation of the present. There is no access to the present of anything beyond your own body. The universe you study, the one humanity has mapped and named and theorized about, is the universe's past, delivered continuously to your instruments at the speed of light, from every direction, for your entire civilization's history. The present universe is made of light that has not reached you yet. It is coming. Every second at 299,792,458 meters per second. In every direction, information about the present is traveling toward you. It will arrive. It will be very old when it arrives. It will never catch up to the actual present, because the actual present is moving forward at the same rate as the light is traveling, which means the light is perpetually chasing a present that perpetually recedes. You will study the universe your entire life. Your civilization will study it for as long as it exists. What you will study, what any observer inside this universe can ever study, is the light that has already traveled far enough to arrive. The present universe is not dark. It is bright, burning, full of events, supernovae and mergers and new stars forming in collapsing clouds of hydrogen, right now, in this moment, in the same moment you are reading this. You will not see any of it. Not because you lack the instruments. Because the light hasn't arrived yet. And when it does, it will already be history.